To start off with, I would like to say thank you for interrupting and asking questions yesterday, and I hope you will keep doing that today. I'm teaching online at the moment, and all my students sit there with their microphones off and their cameras off, saying nothing. It's so pleasant and refreshing to know that there is actually an audience listening to me and asking questions. So please keep on doing that. So today I'm going to be mostly talking about a class of graphs called cographs. Now, I'll define them, and you probably won't see initially why they're important or why I'm making such a big deal about them, but you will. So they've arisen in various times and been rediscovered, and so they have various different names, some of which I wrote here: complement reducible graphs, hereditary Dacey graphs, n-free graphs. But they're a very beautiful class of graphs, and they have important links to the kinds of problems that we're talking about, which is the subject that I'm going to be talking about today. So, here we go. So here's the definition. A finite graph is a cograph if it has no induced subgraph, which is the four-vertex path. So a path with four vertices and three edges. And the four-vertex path graph is complementary. There's a four-vertex path. And if you look at the missing edges, you see they also form a four-vertex path. So it's a self-complementary graph, and that means that if a graph contains no four-vertex path, then its complement contains no four-vertex path. So the complement of a cograph is a cograph. That's the first thing that we can note down. So let's look at this class of cographs. Here are some of its properties. These things, incidentally, these are not difficult, but I'll leave them to you as exercises. You'll get some feeling for this class of graphs if you try these exercises. So if you have a cograph on more than one vertex, if it's connected, then its complement is disconnected. Now, just let's stop and think about that a moment. If you have any graph which is disconnected, then its complement is connected because it contains at least a complete bipartite graph between two of the components of the complement. So for cographs, it works the other way around. So a cograph is connected if and only if its complement is disconnected. And of course, it's also true that a disjoint union of cographs is a cograph. You can't create a path on four vertices by taking disjoint unions of graphs unless they already contain one. So cographs actually form the smallest non-empty class of graphs closed under the operations of complement and disjoint union. And what that means is you can build every cograph by starting with the one vertex graph, and you're allowed to take disjoint unions and the complement of what you've already got. So you could take a bunch of disconnected vertices, take the complement, that's a complete graph, get a bunch of complete graphs, take the complement, build up like that. And so every cograph arises in that way by building up. And it follows from that that the automorphism groups of cographs are extremely restricted. They can also be built from the trivial group by the operations of direct product and taking the wreath product with a symmetric group. So let me say a little bit about that. If you have a disconnected graph, then its automorphism group is, you first of all take the connected components, you divide them up into isomorphism types. Then within each isomorphism type, you have the automorphism group of that graph, the wreath product with a symmetric group permuting the copies around, and then you have a direct product of all the things for the different isomorphism classes. So the automorphism group of a cograph is a direct product of wreath products of automorphism groups of smaller cographs, and so by induction you get that you can build them up from the trivial group in this way. So they are very restricted. And as I said, I'll leave the proofs as an exercise, but let me just say, this gives us a beautiful recursive structure to cographs because they build up from the one vertex graph by these operations.
That's exactly what automorphism groups of trees look like.
It is exactly what automorphism groups of trees look like, indeed. Yes. So automorphism groups of trees are easy to deal with in the same way. So cographs and trees are completely different classes, but they both have this property that the automorphism group can be built in this way. Yes, thank you. So many computational problems that are hard for general graphs are actually easy for cographs because of this recursive structure. So they're one of the nicest classes, simplest classes of graphs. Now I want to turn to something that looks completely different, twins. Two vertices of a graph are twins if they have the same neighbors, possibly excepting one another. So these two vertices are not joined, but in each case, their only neighbor is this vertex over here. These ones are joined, but apart from one another, their only neighbor is this vertex over here. So I'll call both of these types of vertices twins. And part of the reason for doing that is we've seen that cographs are closed under complementation. Well, if you take a graph that has a pair of twins like this, its complement will have a pair of twins like this. So if we're going to get a theory that's invariant under taking complements, we have to take both sorts of twins. And I'm going to distinguish them by calling these ones open twins, these ones closed twins, because in this case, the open neighborhoods of these vertices are equal. In this case, the closed neighborhoods are equal. But now, if you have twins, then you can take the automorphism that swaps the two twins, fixes all the other vertices in the graph. So a very special kind of automorphism. So here we are. These are the two types of twins, which I will distinguish by calling them
It's also called true twins and false twins. Am I right?
Sorry, it's
also called true twins and false twins.
Yes.
It's open twins and closed twins.
Yes. Well, I want to treat them together, and so I've invented my own terminology here. If there is other terminology for it, please let me know. I'm happy to hear that. But being twins is an equivalence relation. This is another easy exercise to prove. And in each equivalence class, all pairs are of the same type, either all open twins or all closed twins. And one way to see that is we take our remark up here that if two vertices are twins, you can swap them over and fix the rest of the graph. That shows you that you can permute each equivalence class arbitrarily. So you get a symmetric group on each twin equivalence class, fixing all the other vertices in the graph. So those are twins. And of course, if we have twins, that not all properties of graphs are like this, but there are many properties which, if you collapse them, the twins, to a single vertex, the property remains true. We'll see examples of this. But so if you collapse a pair of twins, then there might still be twins, so you collapse them. And you go on collapsing until you can't collapse any further. And you get a result, which, to give it a name, I shall call the co-kernel of the graph. This has got nothing to do with homological algebra. This is just a name saying we're in the same line, the same area of graph theory as cographs, as you'll see in a moment. So the co-kernel of a graph is what you get by identifying twins wherever possible. And the result is independent of the way you do the reductions. That's another exercise which is not difficult. Now, here's why cographs and twins are closely connected. A graph is a cograph if and only if its co-kernel is the one vertex graph. In other words, if and only if you can collapse it down to a single vertex by a series of twin reductions. So That's another test for a cograph, actually. Just find a pair of twins, identify them, carry on doing that as long as you can. If you don't get to the identity, it's not a cograph. So I'm going to outline the proof of this theorem. First of all, if you have a cograph on more than one vertex, it contains twins. It has a pair of twins, and the proof is by induction. Your cograph might be a null graph. Well, then in that case, it's clear. But if it's not a null graph, if it has at least one edge, if it's disconnected, then a non-trivial connected component is a smaller cograph and therefore has twins, and they're twins in the original graph. If your graph is connected, then you consider the complement, and we saw that the complement of a connected cograph is again a cograph, but it'll be disconnected, and so this argument will apply. So any cograph contains a pair of twins, and twin reduction preserves the cograph property, because by twin reduction you can't create a path of length 4 that wasn't already there. And in the other direction, if the graph contains an induced 4-vertex path, then the vertices in that 4-vertex path, no two of them can be twins because they have different neighborhoods already in the 4-vertex path. And so a 4-vertex path is going to still be there when you do twin reduction, so you cannot reduce the whole graph to a single vertex. So that's the link between twins and cographs. This is also relevant to the question of graphs with forbidden subgraphs. If you take the class of graphs containing no induced subgraph isomorphic to a given graph F, and let's suppose that F has no pairs of twins, so suppose F itself is twin-free, then you can do twin reduction on this graph that you started off with, the graph in the forbidden class. You can neither create nor destroy an induced copy of F. So if there was one there to begin with, it'll still be there after twin reduction. If there wasn't one, then you can't create one by twin reduction. So a twin-free graph belongs to the forbidden subgraph if and only if, if F is twin-free, then a graph forbids F if and only if its co-kernel forbids F. And here's an example of that, perfect graphs. This is a very important class of graphs. A graph is perfect if every induced subgraph has clique number equal to chromatic number. Now, there was something called the strong perfect graph conjecture for many years. This was a conjecture of Claude Beige. It was proved about 10 or 12 years ago by Maria Chernovsky and others. It says a graph is perfect if and only if it has no induced subgraph, which is either an odd cycle, a cycle of odd length at least 5, or the complement of a cycle of odd length at least 5. And odd cycles and their complements are all twin-free. You only have to check cycles because twins are preserved by complementation. So cycles are twin-free, and therefore we conclude that the graph is perfect if and only if its co-kernel is perfect. And as a particular application of that, cographs are perfect. Now, you can easily prove that directly, but it follows from this because if a graph is a cograph, then its co-kernel is a single vertex, and a single vertex is obviously a perfect graph. So our class of cographs sits inside the class of perfect graphs. So I talked a little bit about this yesterday, but let me say it again. The power graph of a finite group is a perfect graph. That's because if you look at the directed power graph, that's that relation, the relation defined by the arcs in the directed graph is reflexive and transitive, I'm assuming we put back the loops at every vertex here to make it reflexive and transitive, and the power graph is its comparability graph. So it's the comparability graph of a partial preorder. We can replace that partial preorder by a partial order without changing the comparability graph, just by taking the equivalence classes, the relation that says x is equivalent to y if they are x is less than or equal to y and y is less than or equal to x is an equivalence relation in a partial preorder. The equivalence classes are everything is joined in both directions, so we just simply take a total order of each equivalence class, and that gives us a partial order on the whole thing. So a power graph is the comparability graph of a partial order. Now, Dylworth's theorem says it has two parts, the easy part and the hard part. The easy part says that the comparability graph of a partial order is a perfect graph. The harder version, which says that the complement of the comparability graph of a partial order is perfect, is the real important part of Dylworth's theorem. We're only using the easy part here. But
excuse me.
Yes.
Yesterday you concluded with the theorem that the power graph of a group is a comparability graph.
Yes.
And these
that's right.
Cographs, perfect graphs, and bipartite graph, they are all examples of comparability graphs, isn't it?
That's right. That's right.
Okay. So do you
yes.
find any special property of the group which makes it, say, perfect, which makes it cograph like that?
That's a very good question. It's a question that I'm going to be asking in a little while. If you're looking at the power graph, we know that it's a comparability graph and therefore it's perfect, but we don't know about more restrictive properties of it. Is it a cograph or something else? Those are unknown, and I'm going to be talking about those. They're important questions, I think. For other kinds of graphs, we know that for, let's say, the commuting graph or the generating graph, they're universal. Every finite graph is an excuse me, an induced subgraph. So even asking which ones are perfect is a non-trivial question. And those are all very good questions that I'd like to see answers to. So for all the graphs that I've been telling you about, when are they perfect? When are they cographs? I think those are important problems. Anyway, why have I been going through all this stuff about twins? Well, graphs in this hierarchy that I defined yesterday always have twins. The twin relation on any of the graphs that I've been talking about is non-trivial. And this is why. Let's suppose that your group has an element whose order is greater than 2. And then that element will generate, if its order is m, it will generate a cyclic group of order m, and there will be other elements in that cyclic group that also generate, and it'll easily follow that those two vertices, g and g to the power d, are closed twins. Each is well, if we take, say, the power graph, each is a power of the other, and anything that's a power of g to the d is a power of g, and conversely, because they generate the same cyclic subgroup. Now, anything that commutes with g also commutes with g to the d, so the commuting graph, that also works. Also, if g together with an element x generate the group, then g to the d together with x generate the group. So this is also true for the generating graph. So for all of our types of graph in the hierarchy, if there's an element of order bigger than 2, then you will find closed twins. And so the only case that I haven't covered is where there are no elements of order greater than 2. So the group is an elementary abelian 2 group. In that case, you can look directly. The commuting graph is complete. If the order is greater than 4, the non-generating graph is complete. But we saw yesterday that the deep commuting graph is a star. The power graph and the enhanced power graph are also stars, and stars are cographs. Stars have non-trivial twin relations, so that's why this holds for arbitrary non-trivial groups. So groups in the hierarchy always have twins, and so it makes sense to ask, let's suppose you take one of these graphs, and you do twin reduction on it as far as it goes. And so go down to the co-kernel. Then what can you say about that? If you get right down to the one vertex graph, then the thing you started off with is a cograph. And the other reason for looking at this is automorphisms. As I just said, if x and y are twins, then you can transpose x and y, fixing all the other vertices. That's an automorphism of the graph. So that means that if you look at all the transpositions like that, they will generate a normal subgroup of the group, which is a direct product of symmetric groups on the twin classes. And so for that reason, the automorphism group of one of these graphs is likely to be very large. And if you're interested in the automorphism group, you might want to do twin reduction first. And of course, if the graph is a cograph, the twin reduction will take you right down to the trivial graph. But if it's a cograph, then we understand something about the automorphism group. It's built by direct product and wreath product with symmetric groups. I first became aware of this when I was thinking about the non-generating graph of A5. And so I just asked the computer to tell me how many automorphisms it had, and I came up with this vast number. And I was a little bit shocked at first. What does that mean? What kind of group is it? Well, the point is, A5, you have, apart from the identity, you have 10 twin classes of size 2 corresponding to the elements of order 3. We just saw that an element of order 3 and its square make a twin class. And so you get 10 twin classes of size 2. And similarly, elements of order 5 give you 6 twin classes of size 4. So you have S2 to the 10th times S4 to the 6th. And that accounts for most of this huge number. If you factor out that subgroup, you get down to, well, the co-kernel has 32 vertices, and its automorphism group is just S5, which is the automorphism group of A5. And we know that must be there. I mean, so twin reduction often, you know, going down to the co-kernel often tells you, makes the problem of studying the automorphism group more manageable. Except there is another problem that might conceivably arise, and that is when you do twin reduction, you might create automorphisms that weren't there before. If you just go back to that example that I had of graphs that contain twins, if I identify the twins in this graph, I just get a path of length, of a 4-vertex path. So I get an automorphism that wasn't there before, the automorphism that swaps the two ends of the path and the two vertices in the middle. It flips the path over. And so you have to be a little bit careful because extra automorphisms can crop up in the process of twin reduction. And we have some quite non-trivial examples of that. Anyway, so there are always twins in these graphs in the hierarchy. And the automorphism group will give you this will have a large normal subgroup commuting the twin classes. So this is the question that I really wanted to get to. For which groups is it true that the power graph of G is a cograph? Remember, being a cograph means twin reduction. Well, let's say the power graph will always have twins, so you can always do twin reduction, get a smaller graph. If you get right down to the trivial graph, then your graph is the thing you started off with was a cograph. And so it's some interest to know when that happens, because if it doesn't happen, then the co-kernel probably has interesting information about the original graph in it. But if you get right down to the one vertex graph, the only thing you've learned is that the original graph was a cograph. So I'm going to say a little bit about how this problem might be attacked for any of the types of groups in our hierarchy, but I'm going to start with the power graph because that's probably the one that we know most about. So the first thing is, it was perhaps a little bit disappointing at first, but this is a question about connectedness. Now, first let me remark that the graphs in the hierarchy might have isolated vertices, or they might have vertices joined to all others. For example, we saw that if you take the commuting graph, then vertices in elements of the center are joined to everything else in the whole group. And so the center consists of vertices that are joined to everything in the group. And so if you're asking questions about connectedness, it makes sense to remove them. And in particular, if you're asking about connectedness of the complementary graph, then in the commuting graph, elements of the center will be isolated vertices. And again, we'll need to remove them. But let's look at the power graph. It's known what are the vertices joined to all others in the power graph. There are no isolated vertices, but there are vertices that are joined to all others. If G is cyclic of prime power order, then the power graph of G is the complete graph, and therefore everything is joined to all other vertices. If G is cyclic but not of prime power order, then the vertices joined to all others consist just of the identity and the generators of the cyclic group. We went through this example of the cyclic group of order 6 last time, and we said that the vertices joined to all others are the identity and the two generators. If G is a generalized quaternion group, then the involution in the center is joined to everything, and in fact that's all. So in a generalized quaternion group, the set of vertices joined to all others is just the center of the group, just as it is in the commuting graph. And in all other cases, the only vertex joined to all others is the identity. So in most cases, if the group is not either cyclic or generalized quaternion, then the only vertex joined to all others is the identity. So typically we'll say, if you remove the identity, what's left? Is that connected? So in fact, I said these are the vertices joined to all others in the power graph. Therefore, they're the vertices that are isolated in the complement of the power graph. And so this is what happens in the complement of the power graph. For any finite group, the complement of the power graph has a single connected component apart from isolated vertices. So I'm not going to give you a complete proof of that, but the point of it is that if the power graph is a cograph, removing isolated vertices doesn't change the property of being a cograph. And if when you remove the isolated vertices, you get a connected graph, and it's a cograph, then its complement is disconnected. So we know that a necessary condition for the power graph of G to be a cograph is that when you remove the vertices joined to everything, the result is disconnected. Well, I'm going to show you the proof of this theorem, not for the power graph, but for the commuting graph. Now, remember that the power graph, edges of the power graph, the edge set of the power graph was contained in the edge set of the commuting graph. That means when we take complements, it goes the other way around. The complement of the commuting graph is contained in the complement of the power graph. So if the complement of the commuting graph is connected apart from isolated vertices, you add some more edges in. It takes a little bit of work, but it's not too hard to show that from this theorem, you can deduce this theorem. And in fact, the non-trivial connected component in this case has diameter at most 2. So I'm going to show you the proof of this because it's a very simple idea, but surprisingly useful. So let's look at the commuting graph. Let's go back and look at the commuting graph. The closed neighborhood of a vertex, if you take a vertex G and look at G together with all its neighbors, what does that mean? Well, that's all the elements that commute with G. So that's the centralizer of G in the group. And that's a subgroup. So the closed neighborhood of any vertex in the commuting graph is a subgroup. And if the element you chose was in the center, then that subgroup is the whole group. So this element is joined to everything in the commuting graph. So it's an isolated vertex in the complement. So we want to look at vertices that are not in the center. So suppose we take two vertices G and H, not in the center of G. Then the centralizer of G and the centralizer of H, I'm sorry, that should be a lowercase h, are proper subgroups. They're not the whole group because we chose these elements not in the center. And a finite group can't be written as the union of two proper subgroups. If you haven't seen that before, you should try it as an exercise. It's not difficult to prove, but it's the basis for this argument. A whole group can never be the union of two proper subgroups. And therefore, if these are two proper subgroups, and therefore there's an element K outside both, what does that mean? It means it doesn't commute with G and it doesn't commute with H. Therefore, it's joined to both G and H in the complement of the commuting graph. So whatever two vertices we chose not in the center of G, there was a path of length 2 joining them in the complement of the commuting graph. So that proves the theorem that I stated back here. The commuting graph, the complement of the commuting graph, has a single connected component of diameter at most 2, apart from isolated vertices. And as I said, the upshot of that is that we'll be looking for graphs if we're looking for groups whose power graph is a cograph, we're looking for groups whose power graph, once you remove vertices joined to everything, is disconnected. Now, so that's the sort of basis that we're doing. Now let's go on to actually start attacking this problem. There's one case that turned out to be tractable and that we were able to do. So the group is nilpotent. Finite group is nilpotent if it's the direct product of its Sylow subgroups. And here's the theorem that I proved with two people in the audience, Palabhimana and Ranjit Mehtari. We classified all nilpotent groups whose power graph is a cograph. Such a group could be a P group for some prime P, or if it's not, then it's the cyclic group whose order is a product of two primes. So nilpotent groups which are not of prime power order, but whose power graph is a cograph, are extremely restricted. You only get these cyclic groups of order product of two primes. So if we just think back to the cyclic group of order 6 for a moment, remember that in the cyclic group of order 6, if it's generated by little a, the identity a and a to the 5th are joined to everything. When we take them out, we only have 3 vertices left, a squared, a cubed, and a to the 4th. A squared is joined to a to the 4th because each of them is a power of the other. A cubed is not joined to either. So this reduction process will get us to a graph with one vertex and one edge and no connection between. So that's an example. And the general case works in a similar way. So these are the only nilpotent groups whose power graph is a cograph. And why is that useful? Well, it tells us not just about nilpotent groups, but you remember I said yesterday that for any of these types, the power graph, the enhanced power graph, or the commuting graph, if you restrict it to a proper subgroup, you get that group associated with that subgroup. So it says, if the power graph of an arbitrary group G is perfect, then if you restrict it to any nilpotent subgroup, then you must also get a perfect graph. Or a cograph, if we're looking at cographs, this is also true for cographs. I'm sorry, I think I meant to say cographs there. Yes, I meant to say cographs there, sorry. So it tells us that if you have a nilpotent subgroup, which is not one of the Silov subgroups, it must be cyclic of order product of 2 primes. So in particular, you can't have, say, a cyclic group whose order is p squared q or pqr, where pq and r are distinct primes. So it does put quite tight restrictions on an arbitrary group. That's why I think this is a doable problem with finding all the finite groups whose power graphs are cographs. We have that thing to help us. So here's a little problem, just a test problem that we might be able to solve on the way to getting this characterization. So is the following true?
Could you,
so if you take,
excuse me?
Yes, yes.
Could you go to the previous slide, please?
Yes, of course.
So, so if the power graph of an arbitrary group is going to be a cograph, in particular, all its Silov P subgroups must be cyclic.
No. There's no restriction on the Silov P subgroups. If you take any group of prime power order, then its a power graph is a cograph. So there's no restriction on the Silov subgroups. But there is a restriction on the nilpotent groups, which are not P groups, right?
No, but if you pick out the subgraph consisting of its Silov P, say one of the Silov P subgroups,
yes,
that also would have to be a cograph.
That will have to be a cograph, but it is a cograph. Every group of prime power order, the power graph is a cograph. So that's no restriction. We learn nothing about the Silov subgroups directly. The only thing we learn is this fact that nilpotent groups, which are not Silov subgroups, must be cyclic of order PQ.
I see. Okay.
Okay. So yes. So it's a slightly indirect piece of information, but it is very valuable information. But anyway, I propose this problem, which will be a sort of test case to see how we're getting on. Suppose you take a cograph. Well, suppose we're looking at groups whose power graph is a cograph. Is that universal for the class of cographs? In other words, given any cograph, can you find a group whose power graph is a cograph and contains gamma as an induced subgraph? Now we know that this theorem is true if you replace cograph by comparability graph of a partial order. I told you yesterday that if every graph which is the comparability graph of a partial order is embedded in the power graph as an induced subgraph in the power graph of some group, and the power graph of any group is a comparability graph. So that gives us exactly the class of induced subgraphs of power graphs. But if the graph we start off with is actually a cograph, can we embed it in the power graph of a group G such that that whole power graph is a cograph? So that I propose as a test problem. Is it clear what I'm asking? Right, so why is this a tricky problem? Well, first of all, what do we know about cographs? We have this beautiful inductive scheme for cographs. It depends on taking the complement. But what is the complement of the power graph? Well, it's nothing very particularly nice. It's not the power graph of some other group, for example. So taking the complement is not likely to be helpful to us. And the other thing is, the result about nilpotent groups means that there won't be a nice direct product decomposition to handle disjoint unions. A disconnected cograph is a disjoint union of smaller connected cographs, but we can't just embed those in groups and take the direct product of all the groups, because that would have nilpotent subgroups that were not just CP cross CQ. So those difficulties suggest that if we're going to solve this problem, we have to look for a group of prime power order. Now, as I said, if you have a group of prime power order, its power graph is certainly a cograph, always. And therefore, that's the best place to look for a solution to this question. So anyway, that is a little problem that might come up along the way. So let me press on. Let's look at some other groups. What happens for, well, if you like simple groups, first family of simple groups.
Just to understand this, how do we prove that any group of prime power order, the power graph is a cograph? It's because the center is always non-trivial, and we can complement and keep removing the center.
You could probably prove it that way. The way I proved it is if you see, if it failed to be a cograph, you would have to have an induced path, 4-vertex path. And if you look in the power graph of a group of prime power order, you see that if you have, let's say, if x is the power of y, well, let me put it like this. You can look directly, you can say, okay, what are the orders? Suppose you had an induced path on 4 vertices. The orders of its four vertices would have to be powers of p to the a, p to the b, p to the c, p to the d. And you can work out the relationships between those, given that there are also some non-edges in there, and you find that you just can't embed that graph.
I see.
It's not a difficult argument, but it is a little bit tricky, and it's one of the things that we had to go through when we were proving this theorem back here. So you might like to look in our paper and see how it's done there.
Okay. Okay, thank you.
Okay, so is that okay?
Yes.
Thank you.
Yes.
Okay, so let's look at PSL2Q. It's the easiest kind of simple group. So in PSL2Q, you have, what are the Silov subgroups? Well, the Silov subgroup for the prime dividing Q is elementary abelian. It's the additive group of the field of Q elements. But the other Silov subgroups are all contained in cyclic groups of orders, either Q minus 1 and Q plus 1 if Q is even, or Q minus 1 over 2 and Q plus 1 over 2 if Q is odd. So we've got these big cyclic subgroups there. But we know that if the power graph of this group is going to be a cograph, then those cyclic subgroups, the orders must be either prime power or product of 2 distinct primes. And that's extremely restrictive. So this is what we conclude. The power graph of PSL2Q is a cograph if and only if each of L and M defined like this is either a prime power or a product of 2 distinct primes. So at that point, it turns into a number theory question, right? Because Q is a prime power, and we're defining L and M to be either Q minus 1, Q plus 1, or Q minus 1 over 2, Q plus 1 over 2, and we're asking that each of them is either a prime power or product of 2 distinct primes. And so here's a question. This is another, I think, hard number theory question. Are there infinitely many prime powers for which the power graph of PSL2Q is a cograph? So we'd have to be able to solve this number theory problem of you take a prime power Q and define L and M and ask that each of them should be either a prime power or a product of 2 distinct primes. So it breaks up into quite a number of Diophantine type problems, which look a bit like Fermat and Mersenne primes and the Catalan conjecture, but it's not quite the same as any of those. But there are quite a lot of values for which it holds. So if you look at powers of 2 to the d, Q equals 2 to the d, and you ask, for which d is it true that Q minus 1 and Q plus 1 are both either prime powers or products of 2 distinct primes? You get quite a long list of primes up to 200. So, for example, you see if you take d equals 4, 16. Well, 15 is a product of 2 primes. 17 is a prime because it's actually a Fermat prime. And for 5, 31 is a Mersenne prime. 33 is 3 times 11. For 6, it fails because for 6, 2 to the 6th is 64. 65 is a product of 2 primes, but 63 is 3 squared times 7. So it's neither a prime power nor a product of 2 primes. So there's a number theoretic question, which I don't necessarily expect to see a solution of. And there are quite a few odd prime powers that work as well. So here's a list. 3, 5, 7, 9, 11, 13, 17, 19. You notice that 23 is missing. Let's just look at that. PSL2 23, the power graph is not a cograph because what we have to do is take 22 over 2, which is 11. That's prime, that's okay. But 24 over 2 is 12, and 12 is 2 squared times 3, so it's not either a prime power or a product of 2 primes. So what about other simple groups? I'm just going to show you some computational data on this. So I'll give you this, what this table I'm going to show you gives you is the sizes of the co-kernels of all the various graphs in our hierarchy on the first few finite non-abelian simple groups by order. So all the types we've been talking about are in the table. And remember, when you look at the table, that a graph is a cograph if and only if its co-kernel has just one vertex. And so we're asking the question, when does that happen? So here's the data. You see, there are quite a lot of ones in the table. So cographs occur quite frequently in here. But PSL223 is the one that I was just talking about. The power graph of that is not a cograph. Indeed, its co-kernel has 1,267 vertices. But the enhanced power graph and the commuting graph are both, the deep commuting graph are both cographs, though the commuting graph again is not, and neither is the non-generating graph. So it's an interesting table, and as I say, you get quite a lot of ones in it. You might look at this table and you might make some conjectures. The commuting graph, PSL28, PSL216, A5 is PSL24, so you might think, oh, probably the commuting graph of PSL2 to the D is always a cograph. And perhaps if Q is not a power of 2, it's not a cograph. So there are some things you might like to prove. But I'd just like to briefly say a word about the last column, the non-generating graph. You never get one here, apparently. So you might conjecture that the non-generating graph of a non-abelian finite simple group is never a cograph. That's actually true. And the reason is because there are some big results that we can throw at it. Bones, Goralnik, and Harper proved that the reduced generating graph, so if you take a finite simple group, take the generating graph, throw away the identity, this has what is called spread, at least 2. That means any 2 non-identity elements have a common non-identity neighbor. So the generating graph is connected, but also the non-generating graph is connected. This was proved by Shen, but recently Saul Friedman has got the best possible bound for the diameter, namely 5. So both the generating graph and the non-generating graph, once you throw away the identity, they're both connected, and therefore neither of them can be a cograph because the complement of a connected cograph is disconnected. So that at least is true, and that comes out of the table. But you can stare at the table and perhaps see various other conjectures that you might like to have a try at proving. Let me just draw your attention quickly to M11. All of these have the same number of vertices, 1,212. And I think this is probably a nice graph. The automorphism group has only a small number of orbits. And the automorphism group of this graph is actually, well, I haven't checked in all cases, but certainly in the case of the power graph, full automorphism group is just M11, and it has just a small number of orbits. So a nice graph there.
Peter?
Yes.
I just wanted to clarify, unless I'm misunderstanding, unless I'm thinking of something incorrectly, I think what we determined is that for the non-generating graph, the best bound is either 4 or 5.
It's either 4 or 5. I'm sorry. Yes. Okay. So the possibly best possible bound. Yes. I beg your pardon. Yes, you're quite right. That so it should be 4 or 5.
Okay. Thank you.
Yeah. Okay. So it's not a cograph, but how many vertices are there in the co-kernel? If you just look at these, there's no particular pattern to these numbers as far as I can see. In some cases, the number that you see here is the number of cyclic subgroups of the group, because we've seen that the generators of a cyclic subgroup are all twins, so they'll all collapse down to a single vertex. And to say that the number here is equal to the number of cyclic subgroups would say that there's no further collapsing. Once you've done that collapsing, there are no more twins. But that's not true in all cases. It's probably true in many cases, but not all. So that's another question that might be worth looking at. We'd like to know this about the commuting graph as well. I've nearly finished. Let me just talk a little bit about this. For the commuting graph, you can ask the same questions. When is it a cograph? When is it perfect? And there is another tool here, because the commuting graph is nicer than the power graph with respect to direct product. So there's an operation on graphs called the strong product, where you take the Cartesian product of the two vertex sets and you join two pairs of vertices if the first components are equal or adjacent, the second components are equal or adjacent, but to exclude loops, we say that they're not equal in both cases. So that's the strong product, and it's closely connected with direct product. The commuting graph of the direct product is the strong product of the commuting graphs. And if G and H have co-prime orders, then the enhanced power graph does the same thing. And if the derived factor groups, G over its derived group and H over its derived group, have co-prime orders, in particular, if G and H are perfect, then the deep commuting graph of the product is the strong product of the deep commuting graphs. So often you can reduce questions to questions about the Silov subgroups, but there is a problem with cographs. You see, you didn't see cographs there. The strong product of cographs needn't be a cograph, and I'll finish with this. This is just a little example. So it's the strong product of two 3-vertex paths, that one and that one, and you will see that it contains an induced 4-vertex path. So when is the strong product of cographs a cograph? This is a graph theory question that might be needed in some of these problems. So I will stop there. I've run over time a little bit, but thank you for your attention.
Shall I ask 2 questions? Yeah, Arvind, carry on.
No, Vijay, you carry on. You first.
Okay, thank you. You said that the complement of the power graph is not interesting because it doesn't come as the power graph of some other group, isn't it?
Well, I didn't say it wasn't interesting, but
yeah, okay.
You can't. There will be no nice induction that says that you take the complement and you get a smaller group or something like that. So I'm just saying that it's going to be rather tricky working questions like that. So are there other questions?
Yes, I had a quick question, but
yeah, go ahead, please.
So the last slide you showed about commuting graphs, the way the commuting graph of the direct product is the strong product of the commuting graphs of the two groups. So since yesterday, I've been wondering about the realizability question. Namely, you're given a graph and you want to know whether there's a group that realizes the graph as either a power graph or the commuting graph or one of the
Yes.
other two. That's
Yes.
a really beautiful question.
Yes, indeed.
So I was wondering, I mean, if this decomposition can be used to check whether a given graph is the commuting graph of a nilpotent group.
Yes,
Because,
indeed.
yeah, okay.
Because it immediately reduces the question to just looking at groups of prime power order. Yes. I mean, I don't know what the complete answer to that question is, but at least we have good tools for attacking it.
But you would still need to, so you're given a graph and you want to know if there's a nilpotent group that realizes that graph. So you'd still
Yes.
need to decompose the graph as a direct product, unless the total number of vertices is prime power. In
Yes,
which
indeed.
case, so if it's a prime power group, then it should be easy because you can find out the center and kind of keep quotienting it out, I guess.
Indeed, yes.
Yeah.
So yes, I don't know the answer to the question, but as you say, there are tools for attacking it, and so I think it's a nice question and it's a accessible question.
Yes. Okay. Thank you. I'll think about it.
Good. Let me know how you get on.
Yeah, definitely. Yes.
Hello, I'm Hemant Bhate from Pune.
Hello. Yes.
This is sort of related, not quite what you are talking about, but you have never talked about spectral properties of any of these graphs.
No,
Is there something that one can say?
There is a lot that one can say, yes. There is just so much that I could have talked about. I mean, spectral properties is certainly a very important topic, and people have looked at spectral properties of particularly power graphs and commuting graphs, but I don't know if it's been so much looked at for the other types of graphs I've been talking about. Various things are known. I haven't talked about them here, but that doesn't mean that I don't think they're interesting and important.
You see, there is in the case of Cograph, the diameter is less than or equal to 3. Am I correct?
Sorry, could you?
In the case of Cograph, I am
yes.
Selvam. Yeah. In the case of Cograph, diameter is less than or equal to 3.
Yes.
In the case of Cographs, the complement has diameter less than or equal to 2. The group.
Yes,
These Cographs are precisely P4 free graphs.
Yeah.
Yes, C4 or
There are no induced P4s. So the diameter will be less than or equal to 2.
3.
2.
Yeah. My question is, the grid is ultimately less than or equal to 7.
Sorry, the degree.
Grid, the smallest length of the smallest cycle.
The length of the smallest cycle. That's right. Yes.
But very surprisingly, in another class of graphs from commutative rings, namely zero divisor graphs,
yes,
the grid happened to be less than or equal to 5, even though general bound is 7.
Okay.
My question is, can you infer the grid of Cographs independent of this to twice the diameter plus 1?
Well, yes, it's got to be less than or equal to 4, because if you take a cycle of length 5 or more, it contains an induced path on 4 vertices.
Yeah.
So for Cographs, the girth, can't be bigger than 4.
Oh, the induced. Okay.
Right. If you take a cycle of length 5 or more, then 4 of its consecutive vertices will form a path.
Yeah. Okay. Okay, fine. Because I wanted to get into another class of graphs from commutative rings, zero divisor graphs, and so on and so forth. Everywhere it happens to be diameter is less than or equal to 3. My question is this. One more question is, maybe the true. If diameter is less than or equal to 3, automatically it happens to be a cograph, isn't it?
If diameter is less than 3, no.
Why?
So you can take, yeah.
Take the 5
Yeah.
cycle. Take
Okay,
the cycle
fine.
5.
Okay.
Yeah.
I will come to this question in the next lecture. Fine. Thank you.
Okay.
Thank you.
Right. So we have
I had a quick question. This is
yes.
Sandra Kingin. Hi, Peter.
Hi.
Thank you for a nice talk. So I was wondering if the thing about closed twins could be expressed in terms of minors, or is there any connection to minors?
Yes, I thought you might ask a question like that. I don't know. I mean, maybe. I don't see. There's no obvious connection that I can see. But of course, this is a very nice, easy class of graphs to work with. Twin reduction is just such an obvious thing to do with these graphs, and yet I don't know quite how it plays out against various other things like minors. Minors are not self-complementary, though. That's the trouble. All this twin stuff is self-complementary. Cographs are self-complementary. If a graph has twins, so does its complement. But minors don't really behave like that, do they?
Thank you.
So I don't know.
Peter, can I ask something? You
yes,
said
please do.
that the cographs had occurred before and with different names.
Yes.
Right? So how did they, I mean, in what context did they come up? Here you're looking at it in a very, in order to say something about all those hierarchy of graphs using cographs, right?
Yes.
But how did they come up about in the previous situations? What kind of context?
I'm afraid I can't answer that. You've caught me there. I really should know more about the history of that. But one of the names that they were given was hereditary Dacey graphs. Now that means I don't even know what Dacey graphs are, or what makes a graph hereditary Dacey. But I mean that's a good question, and if you looked into that, you might find that there was something in the literature that would have a bearing on the things we're talking about here. But I don't know.
So, fundamental paper is of that of Cornell in 1974, where he looks at properties of graphs which are edge-free. So, as a case, he took H to be path on 4 vertices, and it turned out to be recursively constructed from K1.
Yes.
So that's an easily that becomes an easy class of graphs for computational purpose.
Absolutely.
We have a paper on cographic domination number, that is looking at those subgraphs which are P4 free, and that comes as a dominating set.
Yes.
So several properties of H-free graphs are being studied. So in particular, P4 free.
If we start with a graph and take complements within components, and if that reduces to isolated vertices, then it is a cograph. That is why we name complement reducible. Repeatedly take the operation of complement within components.
That's where that name comes from. Yes.
But Peter, how did you think of this?
Oh, well, this is a class of graphs I've been interested in for a while because, for example, they are comparability graphs of pose sets, but they're actually comparability graphs of what are sometimes called n-free pose sets that don't contain the 4-vertex n-shaped pose set.
Okay.
And that class of pose sets has interesting properties too. In statistics, in experimental design, they have these operations that they call crossing and nesting for building new partially ordered sets from old ones. And the n-free pose sets are precisely the ones that can be obtained from the trivial pose set by crossing and nesting. So I think I first approached it from that direction. But the other thing is they have an important role to play in enumeration, because just the property that if a cograph is connected, its complement is disconnected, tells you exactly how many there are, because if you know the number, if you have if you know the numbers of connected objects in some class, and if you can put them together as disjoint unions, then there's a kind of exponential formula that tells you the total number of things in the class. But for cographs, the total number must be twice the number of connected ones, as long as n is bigger than 1. And so that gives you a formula for the enumeration, and there's some very pretty power series combinatorics involved in that kind of analysis. So that's what I was first interested in, really. There are interesting permutation groups there. So one of my PhD students, Jacinta Covington, managed to construct a countable graph which is P4 free, but is connected and its complement is connected. So this nice decomposability property doesn't hold in the infinite case, and moreover, it's not homogeneous, but close to being homogeneous. So it has a large and rich automorphism group. And her work led on to some very exciting work by people like Eric Neshatril and others about taking a structure which is not quite homogeneous and adding in extra relations to make it homogeneous. So they have connections to infinite permutation groups.
Thank you.
Let me just say one more thing. So I didn't get to the end of the slides I prepared, but I will send you a copy of the slides, and people might want to have a look at that, and you can take a look at the parts that I didn't get to talk about if you're interested.
Yes,
or
yes,
perhaps,
absolutely. Yes.
Yeah.
Perhaps, you might want me to talk about more of this stuff later on in the course of the seminar. I don't know, but
Yes.
in any case,
Yes.
I will do that.
And we'll be thankful if we can give you 1 or 2 lectures more towards May, next, after 2 months or so.
Should be fine. Should be fine.
Yeah.
I've got plenty more to say. Okay, right. Well,
May I call upon Dr. Savita K.S. to officially propose the vote of thanks?
Thank you, Aparna. Good evening, one and all. And we were hearing for the last 2 days, respected Professor Cameron. And he has indeed opened before us a treasure of problems, starting with the very beautiful hierarchy of graphs. So thank you, Cameron, Professor, very much for your wonderful session, and also for the valuable time you are spared with us for these 2 days. And I would like to, I'm very happy indeed to see that you have offered for more sessions for these graphs and groups. So I actually would like to thank in advance for that. So we were very happy to hear you once again during this session on graphs and groups. As Professor Cameron were mentioning about the interrupters of this session, it was really a wonderful thing we had in this session, because that also helped us in one way or the other. So I would like to put a word of thanks for all the interrupters who it
Yes.
also, yes, so it was really a wonderful thing. So thank you all for that. And as usual, our Vijay Kumar sir is always there to promote the young researchers, and he has always been thinking about what can we do for the young researchers. So thank you very much, sir, for this wonderful sessions organized by you, and Aparna for beautifully organizing it. And I also propose my vote of sincere thanks for all the faculty members of Department of Mathematics, CUSAT, for all the support for this organizing this session. Last but not the least, I would like to thank all the participants, and I hope at least one publication will be added to their list. So because it was such a wonderful session. So thank you.
5, not 1.
Okay. So at least one, sir. It's a lower bound only, I told. Okay, sir. So thank you once again. Thank you all once again. Let me conclude. Thank you.
Thank you.
Thank you.
So with that, we come to the end of day 2. The next session will be handled by Professor T. Tamil Selvam, and that will be on 31st March 2021 at same time, same link. So see you all then. Once again, thank you one and all for joining.
Thank you.
Bye.